Here is the equivalent circuit model of the common-emitter amplifier at high frequency. This time around, we are not going to be concerning ourselves with Rout, Rin, etc. We only have to find one thing, FH. And the way to do that is to find V0 over Vsig. Once you find that and put it into standard form, you can identify FH from it and write its expression. So let's start our analysis. We can simplify the left and the right side by using Thevenin equivalence. There you go. The left hand side has been reduced by a Thevenin equivalent, and I mistakenly said that we are going to be using the Thevenin equivalent on the right hand side. No, we are not. We are simply going to calculate the effective resistance, and we find out that RL dash equals parallel combination of R0, RC and RL. We can even simplify it further. Notice this current I mu. The load current IRL dash flowing downwards equals I mu minus GMV pi. Correct? However, at high frequencies, IU can be assumed to be much smaller than GMV pi. And so IRL dash is minus GMV pi. Using this, we can write the equation for V0 minus GMV pi RL dash. I mu can be written in terms of its capacitance and the voltage across that capacitance. Putting in the values, we get this expression. Consider the central figure again. The left hand side of the circuit at x dash knows of the existence of C mu only through the current I mu. Correct? Therefore, we can replace C mu by an equivalent capacitance C equivalent between B dash and ground as long as C equivalent draws a current equal to I mu. Yes? So we write it mathematically. Here you go. And this results in a value of C equivalent equal to C mu multiplied by 1 plus GM RL dash. Now let me show you how this further simplifies our circuit. Here you go. We have separated our circuit into two parts. This makes our derivations very easy. Using C equivalent enables us to simplify the equivalent circuit at the input side to that shown in your figure. Now we can use this simplified diagram and see that the input side is a single time constant STC network of the low pass type. To read and understand further on this, there is a link in the instructor's notes, and you can go and see the different single time constant networks. So now we can express V pi in terms of Vsig bar. V pi is equal to Vsig bar multiplied by 1 over 1 plus SO omega naught. Omega naught is the corner frequency of the STC low pass network. Its value is given by 1 over C in R sig bar. R sig bar is known to you. C in is basically C pi plus C equivalent, which is the effective capacitance, and we know that when capacitances are connected in parallel, we add them. FH is simply omega naught divided by 2 pi. So now we know that our FH is dependent upon C in and R sig bar. Whatever quantities in those two terms we can change, we will do so, and this gives us control over our bandwidth. The multiplication effect that C mu undergoes, that is when it gets multiplied by 1 plus GM RL dash, comes about because it is connected between two nodes whose voltages are related by a large negative gain minus GM RL dash. This effect is known as the Miller effect, and 1 plus GM RL dash is known as the Miller multiplier. It is the Miller effect that causes the common-emitter amplifier to have a large input capacitance C in and hence a low FH. Again, if you see in the instructor's notes, we have a lecture from the MOSFET module where this is touched upon in more detail. You are advised to look at it if you haven't done so already.